Good evening to all. My name is Shiny Pradeepa. I am working as a head of the department in Electrical and Electronics Engineering in PSN College of Engineering and Technology. Today we see about the artificial intelligence in electric power system. So the power system plays major role in electrical engineering studies. It deals with the generation, transmission and utilization of electric power. We know that the power system is a network of electric components that supplies, transmit and use the electrical power to the consumers. Power systems mainly uses the energy resources like coal and diesel to generate the electrical energy. So this is the general structure of electric power system. So we can generate the power by using renewable and non-renewable energy resources. So here we can see the generating system. Normally the generating voltage levels are 11 kV, 33 kV and 132 and 222 kVs. So these powers can be generated by using the renewable and non-renewable energy resources. And normally we know that the generator principle is it converts any form of energy into electrical energy. So once we have generated the electric power, it can transmit to the transmission system. In transmission system there is a two stages. One is step up transformer and second is step down transformer. In step up transformers in step up transformer we are alone using the step up transformer is alone using in the primary transmission side. In why we are using this step up transformer in a primary transmission is we can without changing the frequency and reduce the noises, we are using the step up transformer in the primary transmission side. So next is the secondary transmission systems. In secondary transmission system, the power we can generate we can transmit the power to the distribution side. Here the transmissions in secondary transmission system we are using the step down transformer. So we normally know that in transmission and distribution side there are two stages. One is primary transmission and secondary transmission, and distribution also. This is the distribution side. In distribution side also we have primary distribution and secondary distributions. But in transmission side alone we are using the step up transformer. Remaining three stages, that is secondary transmission and primary distribution and secondary distribution, we are using the step down transformers. So this is the transmission system. We are using the transmissions like these are the supporting towers. We can generate the powers. And finally we distribute the power to the consumers. In distribution side, in primary distribution side, some amount of bulk power is transmit to the industries. So in this picture we can clearly see this some amount of bulk power is distributed to the industries and remaining in secondary side, and the remaining power is distributed to the consumers. So here we can see this consumer side. It can be drawers and house. So this 230 volt and 440 volt is distributed to the consumers. So for single phase means it is 230, and for three phase means it is a 440 volt. So just summarizing the structure of electric power system, that is three stages: generation, transmission and distribution. In generation we can generate the power by using the renewable and non-renewable energy resources, and in transmission side there is a two stages. One is the primary transmission and second is the secondary transmission. And in primary transmission alone we are using this step up transformer, and in transmission, secondary transmission side we are using the step down transformers. And the third stage is distribution side. In distribution side there is the same two stages. One is primary distribution and the other one is secondary distribution. In primary distribution we are using the step up step down transformer, and some amount of bulk power is went to the industries, and in secondary distribution the remaining power is distributed to the consumers. So our main aim is what is the artificial intelligence technique which is applied to the power systems. What is the necessity of artificial intelligence in power systems? So main aim is the power system in distribution side, the power systems are intermittency in nature. Intermittency means it can be the load and the voltage are variable throughout the day. So at this time the load flow methods is not applicable to the distribution side. So that's why we go for the artificial intelligence techniques, because this artificial intelligence is very flexible and adapted to solve the problems, and we can easily access the voltage profile in the distribution side. So in the next upcoming slides, we can see what are the artificial intelligence techniques used in this power system. So this is a normal general conventional load flow methods in the transmission side. Normal conventional load flow methods in distribution side is there are three types. One is Gauss seidel, second is neutron traction, and third is the fast decoupled load flow method. Each has very advantages and disadvantages also. In Gauss seidel, we can see the advantages is it has a quick number of iteration to reach the convergence. But the disadvantage is it depends upon the iteration depends upon the size of the system. If the system size is large, means it took some more number of iteration to converge the load flow solutions. So once the load flow is converged only, we can access the voltage profile. So second stage is neutron traction. In neutron traction, it triggers only very less number of iteration to reach the conversion, but it took more, disadvantages, it took some more computational time, and also the programming logic is very difficult. And third is a fast decoupled load flow method, that is we can name as FDLF method. In fast decoupled load flow method, it has a more number of iteration when compared to the neutron traction, but it is a disadvantages, it is very unsuccessful in the high loaded conditions. So these are the three methods we have used, the conventional three methods used in the transmission side. So what are the limitations of the conventional methods? This conventional methods depends upon the size of the system. If the system size is large, means it took some more number of iteration. If the iteration is large, it means it took some more number of computational time to converge the load flow solutions. And also it has a very complex problem formulation to converge the low output solutions. And also one important factor is ill conditioning. Ill conditioning means all the load flow techniques has Jacobian matrix. So if the Jacobian matrix is 0, becomes 0, then it has a fail to converge the load flow solutions. So this one main drawback is ill conditioning. So if the system is ill conditioned, means it failed to converge the output load flow solution. So the main what are the normal voltage levels in this electric power system is the voltage levels has been defined and classified by various national and international standards, as it has by certain electric power utility companies. So there are main categories, three types. One is low voltage, and second is medium voltage, and third is high voltage. Low voltage means we have termed, how can we term as, means the voltage which does not normally exceeds the 250 volt, means we can term as a low voltage. Then if the voltage is voltage ranges is between exceeds the 250 volt, but it does not exceed 650, means we can term as a medium voltage. And third category is high voltage. High voltage means the voltage which is normally exceeds 650 volt, but it is less than the 33 kV. We can term this high voltage. There is one fourth category. If the voltage exceeds above 33 kV, even if it is under normal condition, we term as an extra high voltage. So these are the four categories: low, medium, high voltage, and extra high voltage. If it is in a three-phase system, means there is three stages: low voltage, medium voltage, and high voltage. In the three-phase system, the low voltage ranges between 100 volt to 1000 volt. If it is a medium voltage, means it is above, it is exceeds the 1 kV, and it is not exceed between the 35 kV, we can term as a medium voltage. Next is, if it is above 35 kV and it is in between 230 kV, means it is termed as a high voltage. So this is the normal national and international standard voltage level in electric power system, both single phase and three phase. If it is a single phase, means it is we can classify it into four category: low voltage, medium, high voltage, and extra high voltage. If it is a three phase, means it can be classified into three types. One, it is a low voltage, and second is a medium, and next is high voltage. Next we can see about the distribution side conventional methods. In distribution side conventional methods, there are four categories. One is Newton downhill, second is current injection method, and third is the hybrid SP. SP means superposition method, hybrid superposition method, and fourth is a forward backward sweep method. So we can now see what are the advantages and disadvantages we can in the conventional load flow methods in the distribution side. In Newton downhill, the advantages is it is independent to the initial solution and it has a very good convergence rate when it is compared to the Newton traction method. We can already see what is the Newton traction methods in the transmission side conventional. And the disadvantages means if the Jacobian matrix is singular, that means is 0, it is a fail to converge the load flow solution. There is the one main drawback in the Newton downhill. Next is the second method is a current injection method. In current injection method, the advantages is it has a very good convergence even in the high loaded conditions also, but if the distribution generation number is high means it is a fail to converge the solutions. And third is hybrid superposition method. It has a very good advantages. It does not need any Jacobian matrix, but if the disadvantages, if the distribution generation is high, that is if the size of the distribution generation is high means it is a fail to converge the load flow solutions. Next, fourth method. This is the most common method used in the distribution side conventional load flow technique. That is a forward backward sweep method. In forward backward sweep method, there are many advantages. One is it does not need any Jacobian matrix and it does not depends upon the PV and distribution generation number, and it is more suitable in online and offline also. But the main disadvantages is it is very unsuccessful in the high loaded condition. It is also it is a very unsuccessful to the large scale networks. So these are the four most commonly used methods in the distribution side power system. So next we see about what are the artificial intelligence techniques which is applicable in the distribution power system. So the first method is a genetic algorithm method. In genetic algorithm method, the main advantage is it is very simple to implement and it has and it is also suitable for the offline problem also. But the disadvantages is in a complex network, it has a very high number of computational time to converge the solutions. And second is a particle swarm optimization. In particle swarm optimization, also it is suitable for the offline also, and also it is very faster when it is compared to the genetic algorithm. But the disadvantage is it is a very slower convergence and it is very unsuccessful in the complex network. And the third is fuzzy logic. In fuzzy logic means it's very simple to implement. It has a very high precision and rapid operation, but its disadvantages it for more accuracy we had a more number of fuzzy rules. So if we generate a more number of fuzzy rules means it took more number of computational time to get the output solution. So next we see about what are the methods already researchers discovered in AI using this in distribution power system. So first we see about the adaptive, this paper, the paper title is an adaptive distributionally robust model for three-phase distribution network. This paper was published in IEEE Transaction on Smart Grid in the year 2021. The author is Wang Swang and Wang Han and David J. Hill. Here the main method they are using is adaptive distributionally robust model is here they took the standard system of IEEE 33 bus system and they are using the distributionally robust model for three-phase unbalanced DNR to identify the optimal configuration. So the main drawback they are using is the proposed method is here the computational time is very high. I can tabulated this computational time with the iterations also. Here you can see for 2 iteration it took 71 seconds to obtain the optimal solution. And also if it is a 8 if the iteration number is 8 means the convergence time is 95.91 seconds to converge the output load flow solutions. In this second paper, the paper title is a physics aware neural network for distribution system state estimation, and this paper was published in IEEE Transaction on the Power System in the year 2020. Here we can see this proposed method is a novel learning model for real-time monitoring the distribution network operation. Here they are using the IEEE 37 distribution feeder, and the proposed model they are using is a greedy algorithm. This is artificial intelligence they are using the greedy algorithm for monitoring the distribution network operation. And the third is machine learning based real time monitoring of long term voltage stability using voltage stability indices. This paper was published in IEEE Generation, Transmission and Distribution in the year 2020. Here they are using the two systems for the proposed methods. One is IEEE 14 bus system and another one is IEEE 118 bus system. The proposed they are using method is machine learning approaches used to predict the long-term voltage stability margin and represented by the load ability margin techniques. Here this proposed model they are using only the selected set of voltage stability indices as an input to evaluate the voltage profile. And also this proposed method utilizes a machine learning based regression model which uses only selected set of voltage stability indices as an input to evaluate the output voltage profile. Next, fourth is the effect of suitable network modeling in voltage stability assessment. This paper was published in the IEEE journal in 2019. Here they are using time domain simulation on the simple system which shows the different reasons may occur on the occurrence of the voltage instability. The software they are using is a DigiSilent software. This DigiSilent software is used with the changes in the transmission and distribution impedances and tap changer limits also. In all the cases, the loading factors increased until the voltage collapse is observed. The voltage stability assessment can be done using the static analysis with the replacement of the distribution network by the suitable load model. And also there's a load ability, the loading limit of the distribution and transmission network can be calculated separately, and whichever is a smaller can be considered as a system loading limit. And fifth paper they are using is a neural network model, neural network based load modeling, and its uses in the voltage stability analysis. This paper was published in IEEE Transactions on Sustainable Energy, and here we can see they are using IEEE 14 bus system, and the proposed software they are using is a neural network for dealing with this both static and dynamic load modeling. Here we can see that both the static and dynamic load voltage stability analysis are performed, which includes the use of neural network based load model. And the static load model may not be suitable for this load dynamics, while this dynamic voltage analysis is too time consuming, which will affect its effective on online views and also for the voltage stability indices. So this static voltage indices may not be sufficient, but the dynamic voltage indices which may be needed in some cases. Next, the paper is linear three-phase load flow for the power system. This paper was published in IEEE Transaction. Here they are using IEEE 37 node test feeder, and this linear power flow for a power distribution system is using the rectangular formulation, and this methodology demonstrated to be valid for both balanced and unbalanced power systems. And the algorithm they are using is a conventional forward backward sweep algorithm. We already discussed about this forward backward sweep algorithm, and this proposed linear model flows gives relatively very low error even also in the high loaded conditions. Next, the new software is a open source power system analysis toolbox. We call it as a PSAT toolbox. So this PSAT toolbox is very helpful for this nowadays in electric power system. So this PSAT was developed by Professor Dr. Fedra Milano. This PSAT is essentially initially is a free software tool in the field of power system analysis. This PSAT is also provided with this complete set of user-friendly and graphical interfaces and Simulink-based editor with one online network diagrams. This PSAT includes many techniques, that is a power flow, continual power flow, optimal power flow, small signal stability analysis, and time domain analysis, as well as we can use for also static and dynamic models, including non-conventional loads and synchronous and asynchronous machines and regulators and factors and fact devices. These are all features which is involved in this PSAT toolbox. So this PSAT power system simulation involves a wide range of time frames. which is starting from microseconds when simulating the fast electromagnetic transient, and it is exceeding to several years of power system planning. This power system may have modeled and solved in different ways depending upon the studies. And this PSET also, this PSET toolbox we can use in this following softwares: MATLAB toolbox, power system toolbox, and electromagnetic transient program, and power system analysis toolbox, voltage stability toolbox, and power analysis toolbox, educational system toolbox we can term as EST, and sim toolbox, simulation toolbox we can term as SPS. Among this PSET, Math Power and PSET VST are the open source and freely downloadable. We can download it and we can use this in the we can install in the MATLAB software, and we can run for the simulation purposes. This MATLAB toolbox is used in the power system analysis, including the set of application features. This can collect the inputs and provide the output in the form of proceedings, and this software was designed in this 2011, and it was first published in the year in November 2002, and this is a free software. We can both for both the static and dynamic analysis also. Once the power flow is done, we can evaluate this voltage profile. All the operations can be assessed by using this GUI, that is graphical user interface. And here also there is a Simulink based library, and it's a very user friendly, and this has various several features, that is a power flow, continual power flow, optimal power flow, and small signal stability analysis, and time domain analysis, and phasor measurement, and graphical user interface, and graphical network editors. These are the features included in this PSET MATLAB toolbox. So this I have developed this diagram with the help of practical Tirunelveli distribution substation in my research, and I am using the PSET toolbox also. So you can see this, I can draw this feature by using this PSET toolbox only. Next we go for the artificial intelligence techniques. So two main, one is fuzzy, and this generalized regression neural network is a very commonly used method in this power system distribution side. So this we can call it as a radial bias neural network. This neural network was developed by D.F. Specht in the year 1991. We can use this neural network in the online dynamic systems, and we can also use for both non-parametric and parametric regressions. Here there are three stages: one is regression, prediction, and classification. And this GRN software can be implemented in many languages, many software languages like MATLAB software, and R programming software, and Python programming languages. We can install this neural network in this MATLAB in this softwares. And what are the advantages in this neural network means there is no back propagation, and it has a very high accuracy, and it has a very less number of data sets to evaluate the voltage profile, and it has a very good accuracy when compared to binary programming neural network. When compared to the generalized regression neural network, it has a very good accuracy even with the noises also. So this is the general diagram of the GRN neural network. I have tabulated this. So this diagram I have used in my research. So here we can see one input box, and this blue color shows the generalized regression neural network, and this third box shows the displayed the output voltage profile. Here we can see this output voltage profile, and in the constant box we can double click this constant box, and we can give the input values, and after the generalized regression neural network operation we can run the Simulink with very less computational time, and also with the reasonable accuracy we can evaluate the voltage profile. This voltage profile is displayed in the display box. So this artificial intelligence can be used in this power grid to improve the operational efficiency, and also to increase the flexibility, and also to reduce the risk of the blackouts. This AI can help with various variety of tasks. that is such as monitoring, that is we can monitor the energy usage and detect the anomalies and provides the real-time data on the power consumption. And the second is predicting. Predicting means AI can predict demand and power supply fluctuations and forecast the power energy demand and supply also. Third is optimizing. Optimizing means AI can optimize the energy resources and it can control the specific power grid operations. And fourth is integrating. AI can help to integrate the renewable energy resources into the power grids such as solar, wind, etc. And final stage is responding. AI can respond to vulnerable parts of the power grid such as rerouting the power or storing any surplus energy. So how AI can powering this today's smart grid technologies. So this AI is a network that integrates energy distribution and digital communication technology in a two-way flow of electricity and data. This enables utility companies to optimize the generation, transmission and distribution of the electrical power, and it also allows the consumers to benefit from the stories and all the data is telling, which is helpful them to better understand the energy which can use, and even the energy can produce and store the things like solar panels and also in EV batteries. So what is the difference between the traditional grid and the smart grid? The main difference between the traditional system and the smart grid is the ability to exchange the information in both directions across the network, from utility companies to the consumers, and also from vice versa, consumers to utilities and utility to consumers, vice versa. So some of the top features that differentiate the traditional and smart grid is, one is technology, that is artificial intelligence, cloud computing, digital technologies, which allows all the devices and assets within the grid to communicate and supports a better control and self-regulation. And second is a distribution. Energy generated by the prosumers and other renewable energy sources such as wind, solar, which can be intermediate and uneven. So the smart grid technologies help to coordinate and store and distribute the power to the consumers from sources like wind and solar, etc. And it is very reliable also. Next, third stage is generation. We can predict, that is predictive analysis in the smart system, which means that high demand strains that can be forecasted and distributed to the multiple plants and the substations. And fourth is sensors we are using in the smart grid. In smart grid we are using IoT sensors. IoT sensors across the network can help to detect risk earlierly and redistributing the power to decrease the outages and help to balance the load without a direct intervention by the operators. And next is self-repair and predictive maintenance. That is, sensors can also be used to detect the mechanical problems and do simple troubleshooting and repairs, and which is notifying the technicians only when necessary, but that is before anything actually break down. And also for customers' choice. Nowadays the more energy suppliers and cooperatives and micro generators can join this smart grid, which allows the consumers to have more choices in how they receive this energy. So the applications of artificial intelligence in smart grid solution. So the artificial intelligence is a driving intelligent agent behind the smart grids. It can evaluate the environment and taking action to maximize to achieve the goal. AI is the fundamental to integrating of renewable energy, and it can stabilize the energy network and a reduction of financial risk associated with the instability with the infrastructure. How today utilizes this industry in preparing for smart grid of the future? So we can see there is a communicating a vision of the smart grid and aligning the teams and stakeholders. We can strengthening this consumers education about this changes and opportunities in the smart grids, and we have to provide awareness, that is motivation for the consumers and prosumers and potential distribution partners, and we to develop matrices to monitor the progress which we have implemented in the smart grid, and how it is how was the effectiveness in the smart grids. And to keep these customers experience and customers retention in mind, we have given the additional competition and decentralization of the smart energy market. So I summarizes this what are the artificial intelligence techniques we have used this in power system is there are many methods we can see, that is genetic algorithm, particles optimizations, neural networks, there are various methods and fuzzy logics, various available methods used in this distribution side load flow. So what is the necessity of AI to develop this artificial intelligence is because normally the power systems are intermittency in nature. Intermittency means it is a variable, it is the power is variable throughout the day. So at that time the conventional method is a fail. If it is a conventional method is not suitable to evaluate the voltage profile, because the conventional method has so many drawbacks. That is air conditioning problem and Jacobian matrix, and irrespective to the size of the system, and it has a more number of computational time to evaluate, to converge the solutions. So that's why we go for this artificial intelligence. So artificial intelligence is very flexible and irrespective to the size of the system, and it has a very good accuracy to evaluate the voltage profile. That's why we go for this artificial intelligence. So in upcoming years this artificial intelligence plays a very vital role in the electrical power systems, even in the smart grids, to assess the voltage profile. Thank you.